Throughout these tutorials there are many instances where plotting is done. What I'm going to do now is show you an example of plotting under chemical kinetics, in which we'll show the effects of the steady-state approximation. What I'll do is I'll be quiet now and I'll let the voice comments within the tutorial continue. I'll start out by clicking here on Plot Kinetic Equations.
Here you can study the most important reactions and steps found in many mechanisms. You can change the rate constants. You can change the concentrations. You can find when equilibrium is attained. You can find the half-lives. If your plot does not fit, you can change the variables and click on the numbers in blue on the axis and change these. In studying these reactions, look at the suggestions on the pull-down menus and follow these. Also on the pull-down menus, you can find all the equations used to plot these reactions.
Let's now go down to the consecutive first-order reactions, in which we can change the parameters and see the effects of different rate constants.
Many chemical reactions have a rate-determining step. If you choose K1 to be about 10% of K2, then the first step is slow or the bottleneck. This is called the rate-determining step. A common approximation in chemical kinetics is the steady-state approximation. To see this, choose K1 as 0.05 and K2 as 0.5, that is 10 times bigger. Then see when you plot the results, the B concentration is about steady for much of the reaction. You should be sure that you understand the rate-determining step and the reason why the steady-state approximation works.
Well, before I change the parameters, let's just go down and plot the kinetic equations with the parameters that I've chosen. And these parameters show you, first of all, that with these rate constants, what we have is A going to B going to C in the consecutive first-order reaction. So A will decrease with time, B grows, and then decreases as B is changed into C. So we could continue plotting. Let's continue plotting, and we will find equilibrium will be eventually satisfied. Let's plot again. Now we're going from 20 to 30, and indeed we find that equilibrium has been attained because there's no change in concentration. Now let's go back and change the parameters here. We said that we should use 0.05 for K1 and 0.5 for K2. Now let's plot with these new values. Now in this particular case, we see that B is small and about a constant. A is still decreasing, but is changing very slowly into B, but then very rapidly into C, because K1 is much less, 10 times, than K2. Let's continue plotting. So I'll plot a little bit more, and now 20 goes to 30, 30 goes to 40. Well, that's going down a bit slow, so I think what I'll do is I won't plot anymore, and I will not get the slope, and I'll change this to a 0, and I'll change this one to about 100. Now you can see the effects of the steady-state approximation because B is a constant throughout most of the reaction. I'll just continue plotting once more. So we see eventually that equilibrium is attained.